My name is Diep. Today I will talk about our work at PLDI. So work is about efficient handling of string number conversion. Here is a structure of our presentation today. We can start with why do we need a string server? And then do we really care about solving string to number conversion? After that, we will present about the language constraint we support in our string solver. After that, we present how we solve the string number conversion. And the last part of the presentation will be the result of our work compared to some state of the art. Let's start with the first one. Why do we need a string solver? First, because we can use string solver for a lot of things, such as for verifying or testing some program using some programs with string variables. As you might know that all popular programming languages nowadays support strings, such as JavaScript, Python, Java, and so on. And it's worth mentioning that string theory for SMT solvers is a new area and developing very fast nowadays. We have a lot of string solvers out there. There are some well-known SMT solvers. They do support strings like Z3, CVC4. There are some younger SMT solvers like Charles, Slot, or Ostrix. They have some string theory and they are very good string theories also. However, there are some limitations of those string solvers, such as the first one is some string solvers do not support all string functions, like Charles, Slot, or Ostrix currently do not support string to number conversion. And some of the solvers are not stable. They can be wrong in some cases. And the performance issues of the string solvers is the one I could mention also. For example, even like we try those string solvers in some simple and short test cases, and we expecting that so tests can be handled quite quickly, but actually it might take some long time. Yep. Next, why do we need to care about string to number conversion? First, because a string to number conversion is a part of programming language called semantics. Second, because of string to number conversion is one of the string functions that we use the most. Here I show you two lines of code. They are very simple. The code is about, I have a for loop. Inside the for loop, I will assign array at I equal to 1 with I from 0 to 10. And we will see if we have any string variables here or any string number conversions. At the first glance, it looks like we don't have any string variables as well as any use of string number conversion. But actually we do. According to the JavaScript core semantics, when we have array at I, so inside the compiler, for example, it always use some function convert from string to int or into string for variable I, as I is an array index of array. Now we have a closer look at how array codes in JavaScript. In my left hand side, I have some code. I have array X, and my right hand side, I show the values of array X. So for example, when we have X equal to 0, 0, 0, then the value of X will be 0, 0, 0. Now when I assign X1 equal to 2, then I have the value of X at 1 equal to 2. It's quite simple, right? Yep. it's going to be a little bit more complicated when I assign x a string of 2 equal to 3. Then I will have the value of x at 2 equal to 3, because string of 2 will be converted to number 2. Now I will have a little bit more complicated. X of string 0, 1 equal to 2. You might think like we will have the value of x at 1 equal to 2, right? But it's not true. We're going to have x still be 0, 2, 3, and we're going to have x at string of 0, 1 equal to 2. So here we actually do not replace 0, 1 to be 1. And the last part, when we have x of string of 0, 2 minus 1 equal to 3, so we will update value of x at 1 equal to 3. Now, as we can see, it's very tricky to understand some JavaScript code because of string number conversion. That's why we need string solver, and those string solver need to support string number conversion to help us figure out some issues, some bugs in our code, especially in our JavaScript code. And the next part of our talk will be string constraint language we support in our string solver. Now, to make the talk be simple, I just mentioned here some string function we support. So the first one is a string equation between string and strings. So for example, we have S1 equal to S2, where both of them are string terms. We also support some linear constraints like length of S1 plus length of S2 equal to 10. Furthermore, we support some language constraints over some string variables, like S1 is a language of 42 star. And of course, we support string number conversion functions. Now, there are two types. First, we have convert from string to number, and the second, we have convert from number to strings. Now we dive to the main part. How do we solve string number conversion? Of course, there are two types, convert from string to number, and the second is from number to string. To make the talk be simple, and of course, we can solve both the constraints in the same way, we can focus on explaining how converting from string to number is done. Now we will solve the constraint to convert from number to string. Let us have the first try. Assume that we don't have any trick to solve it. Call m equal to the length of s. So we can rewrite s equal to c1 to cm with all ci's from 0 to 9. Now we can have the value of n equal to constraint over here. To solve it, that means we need to find the value of C1 to Ci and the value of m. What happens if we ask some SMT solver to help us find the value of Ci and the value of m? Here I rewrite the constraint a little bit to make it simple. I replace n equal to 10, and then I ask Z3 help me to find out the value of C1 and m. So when I ask it, Z3 answer me unknown. So what happens? It's not really because of Z3 is a bad SMT solver or something like that. Actually, Z3 doing very well. The reason is the problem of solving the constraint when we have something like polynomials and exponential is still open. That means we have no way to find the value of C1 and m in this case. So our first try do not go well. Now let's try it one more time. when we restrict the domains of string S using some technique called flattening, we do have the describe of the technique inside our work, so please check it out. For example, when we use the technique flattening, we will limit the domain of S equal to some simple automata loop. Here I limit the domain of S to V0, V1 star, with V0 and V1 is some variable from 0 to 9. And when we write that way, we can have the value of S can be anything like 42 star, 22 star, 98 star, or something like that. When we do limit the domain of S, we will have the value of N as we write here. And once again, this constraint still face the polynomial and exponential problem. So no way we can find the value of V0 and V1. Now we realize that we had to limit the domain of S so that the constraint over variable N will be some linear formula. How can we do that? One of the ways is to bound the length of variable S. Let's say M is a length of S where M is some constant variable, some constant number, can be anything like 1, 2, 3, 4, 5. And then when we know M, we will have some length width of S. So S can be V0 to Vm minus 1, where Vi is some number from 0 to 9. And when we do that, we have some constraint over N is some linear formula, like V0 equal to 10 power of M minus 1 plus until Vm minus 1. And of course, when we give the constraint to some SMT solver, they will have us find out the value of V0 to Vm minus 1. But one thing we don't feel happy about this way is that we had to bound the length of our string variable. And it doesn't work in some cases. For example, when we have the constraint two number of S equal to 10 and length of S equal to 10, and assuming we bound the value, assuming we bound the value of our string variable equal to 5, so M equal to 5, the string solver will return unsat. But actually, the constraint should be sat because we do have the value of S equal to 0, 0, 0, a lot of 0, and then we have a 10 in the end. Let's look at our last attempts. Now we realize that we have two constraints we want to achieve here. First, we want to restrict the domain of our string variables, such that the constraint our numeric variables will be some linear formulas. And we don't really want to bound the length of our string variables. So we come up with a new technique called flattening of string number conversion. What does it mean? That means we can define some constant M, and then we restrict the domain of our string variable to this form. We start with some zero loops, followed by some M nodes, and then we will have the constraint over numeric variable will be like this. And of course, when we give the constraint to some SMT solver, it can solve it. And now we take a look at our example before. We had the constraint two numbers of string S equal to 10 and length of S equal to 10. Now we can have M equal to 5 as we had before. In this case, we still can find the value of our string variable. So we have S equal to 0, 0, a lot of zeros, followed by number 10. It comes to the last part of our presentation today. In this part, we will compare our work with some state-of-the-art on some string benchmark. First, the string server, our string server named Z3 Charles, it is built on inside Interceptor Z3. We have run our work on many standard benchmarks as well as some string to number benchmarks, and indeed it has a lot of test cases. It's worth mentioning that inside the test cases we have run, there's a wide range of string function uses, such as concatenations, length, indexer, and of course, string to number conversion. Here is a table where we compare our string server Z3 Charles with the others on the standard string benchmarks. You can see that Z3 Charles has the best number in the first benchmark. Z3 performs the best in the second one. CPC4 is the best server on the third benchmark. And now when we sum up the numbers, we can see that Z3 Charles has the best number among the others. Here is a table where we compare Z3 Charles with the others on string to number benchmarks. And you can see that Z3 Charles has the best number among all the benchmarks. Of course, CPC4 perform also quite well, and Z3 also do the same. Yep, that's it for our presentation today. Thank you for your attention.